All right, we're looking at Chapter 3 test over probability today. When you have probability, it's the number of desired divided by the total number. Okay? When you do this, when you do probability, your probability has to be between 0 and 1. It can be 0. It could be 1. It could be anything in between it, but it can't be less than 0 and it can't be greater than 1. So in these first couple problems, which of these cannot be a probability? This one right here just points right off here. That's negative. You can't have negative. And right here on this one, 4/3 is more than 1, so you can't have that. These others are okay. If you divide this out, you'll see it's between 0 and 1. All right, so those are probabilities. All right, now on this one, a single 6-sided die is rolled. Find the probability of rolling a number less than 3. All right, less than 3, you're looking at 1 and 2. So you have 2 of those out of 6, which is a 1/3. So that would be this. Okay. What about this one here? Study of 1,000 randomly selected flights of a major airline showed that 725 of the flights arrive on time. What's the probability of a flight arriving on time? So that'd be 725. That's what's desired here, or favorable, either way, over 1,000, and then you simplify it down. All right, you can just use a calculator like this one here. If you type it in, 725 divided by 1,000, you get this decimal here, and you just change it to a fraction, which is 29/40, and it looks like this one. Okay, so these are not too hard. Number 5, if one card is drawn from a standard deck of 52 playing cards, what's the probability of drawing an ace? All right, probability of getting an ace, well, there's 4 aces and there's 52 total. That simplifies to 1/13, which is right there. Okay, number 6 here. In a survey of college students, 847 say they have cheated. And 1,728 said they have not. So these have not, these have. All right, if one college student is selected at random, find the probability that the student has cheated. All right, so 847 have cheated, but on the bottom we're supposed to have total. So I need to take these two numbers, I need to add them together. That's going to be 1517, 15, 2575. So there's my answer right there, A. Okay, remember the bottom number is the total. Top number is what's favorable or what's desired. The bottom is total. What about 7? The distribution of blood types for 100 Americans is listed in the table. If one donor is selected at random, find the probability of selecting a person with blood type A positive. All right, well, there's 34 A positives. How many total are there? So we add all these up. So it's going to be 40, 87, 93, 103, 105, 110. Did I add that right? 40. Yeah, I did 77. That should be 100. Yeah, I accidentally added wrong. So that'd be 0.34 right there, D. Okay, you got to make sure you add them right. All right, number 8. The distribution of master's degrees conferred by universities is listed on the table. So you have 216 mathematics, 207 English, and so on. What's the probability that a randomly selected student graduating with a master's degree has a major of engineering? All right, well, there's 89 engineering, so that's what's desired for this problem. And then we add all these up for total. Let me punch this in real quick. I've got 216 plus 207 plus 89 plus 176 plus 222, and I get 910. All right, well, we got to divide them down, see what decimal that is. So 89 divided by 910, and I got 0978 978, which is 0098. And I don't see it. Maybe we added these up wrong. 216, 207, 89, 176, plus 222. That adds up to 910. So 89 divided by 910. 098. Oh, it's right here. I'm not even seeing it. I'm looking through this lens here, and I'm not seeing them good. All right, so go to number 9. Stem and leaf plot for the number of home runs hit by 30 high school teams. There's 30 of them. Find the probability that a team chosen at random hits at least 24. That means 24 or more. All right, so 24 is right here, and then all these are more. So we just add all them up. All right, there's 24 of those. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. There's 24 of those out of 30. It just happens to be the same number there, but that's coincidence. So this simplifies to 4/5, which is 0.8 right there. Okay. Number 10, sports team has a 3-game road trip. Use a tree diagram to answer the question. List the outcomes of the events if they lose at least one game. All right, if they lose at least one game. Now, if you remember, that's the complement that they win all their games. If they lose at least one game, they lose one or more. That's the complement of winning all of them. So I'm thinking it's this one. Yep, see, here's winning all of them right there. We don't want those. I think it's A. Now, if you remember, there's 3 things here. You can win or lose. So there's 2 possibilities. You can win or lose the second game. You can win or lose the third game. So 2 times 2 times 2 is 8. So there's 8 outcomes you could have. So winning all of them would be one outcome that would not work for this. So 8 minus 1 would be 7. So you see there's 1, 2, 3, 4, 5, 6, 7 right here. It has to be that one. And of course, here's what the tree diagram would look like. Okay. All right, number 11. Determine the number of outcomes in the event. Then decide whether the event is a simple event or not. The computer is used to randomly select a number between 1 and 1,000. Okay. Event A is selecting a number greater than 600. Okay. So, looking at this, we're going to have a number between 1 and 1,000, selecting a number greater than 600. I guess there's 400 of those, so it's going to be B or C. Now, is that simple? Nah, it's not simple because there's more than a single outcome, so it would be C. Okay. About 12. Determine the number of outcomes. You randomly select a computer from a batch of 50 which contain 3 defective. Event B is selecting a defective computer. How many of those are? Well, there's 3, so it's got to be 3 since there's 3 defective ones. That's not simple because it consists of more than a single outcome, so that'd be B. It's not simple. Simple, it only has one outcome. 13. Use a fundamental accounting principle. A shirt company has 4 designs, each of which can be made with short or long sleeves. There are 6 color patterns. How many different shirts are available? So it looks like we have design. Then we have the sleeves. And then we have colors. So we have 4 designs, we have 2 kinds of sleeves, short or long, and then we've had 6 colors, it says. So I just multiply these together. So 4 times 2 is 8, times 6 is 48. There's 48 different kinds you could have. All right. About 14. Use fundamental counting principle again. How many license plates can be made consisting of 3 letters followed by 2 digits? All right. 3 letters, which there's 26 letters. So these first 3 have to be one of the 26 letters, and these last 2 be the digits, which there's 10 digits. Okay, so we just multiply these up. Now I can't do that multiplying in my head, so I'm going to punch it in the calculator. So I have 26. I'm going to go ahead and type to the 3rd power times 10 to the 2nd power. Oops, messed up. 26 to the 3rd power times 10 to the 2nd power. All right, 1,757,600. Looks like this one right here, B. Okay, so that's how you do that problem. 15. Use the fundamental counting principle again. How many different codes of 4 digits are possible if the first digit must be a... Right, let me do this. The first digit must be 3, 4, or 5. So there's 3 possibilities for that first digit. And the code may not end in 0. So in this last number, it can't be 0, which means there's only 9 digits for that. So we can have 10 digits here, 10 possible ones here, it looks like to me. So if I multiply them up, 3 times 10 is 30, times 10 is 300, times 9 is 2,700. Okay, A. 2,700. Okay, number 16. Classify the statement as an example of classical, empirical, or subjective probability. The probability that interest rates will rise during the summer is 0.05. Okay. Let me find my notes here to explain what these are. Okay. Classical probability is what you would expect to happen based on the numbers, but it doesn't always go that way. Okay. Empirical probability is what you have on an experiment. Okay. This is when you have an experiment. This is what you expect. And then subjective, this is based on experience or knowledge. Okay, so this interest rates they think will rise during the summer, I think it's based on experience or knowledge, so this would be subjective. Okay. Now, 17, classify this statement as an example of classic, empirical, or subjective. In a lottery, a person selects a 3-digit number. The probability of winning is 1 over 1,000. All right, that's classical. See, that's just what you would expect to happen based on the number. That's based on the numbers. Okay. All right, now, number 18. If this is a probability, what's the odds? All right, now remember, odds was what, favorable to what's unfavorable. All right, so on this one, 3 on the top is what's favorable. Now the bottom is the total. So if I subtract those two, 5 minus 3, I get 2. That's what's unfavorable. So there's what my odds would be, 3 to 2. Looks like A. Our number 19 is asking, a card is picked at random from a standard deck of 52 playing cards. Find the odds that it's not a heart. Find the odds that it's not a heart. Okay, so probability that it's not a heart. All right, there's 52 cards, and then there's 13 hearts. So if I subtract those, that's 39 that are not hearts out of 52 total. All right, so what's favorable is 39. What's not favorable, if I subtract these, would be 13, and then that comes up to 3 to 1. So the answer is B, which kind of makes sense. You have you have 4 different suits. You have hearts, diamonds, clubs, and spades. Here's your 4 different kinds. So if you do not want a heart, it's going to be 3 to 1. So you could just look at it that way. What about 20? Use a frequency distribution below that shows the number of voters in millions according to age to find the odds that a voter chosen at random is in the given range. All right, so here's my ranges. All right, the odds of voter chosen is not 18 to 20. So here's 18 to 20 right here. Not would be all these. So we want all those because that's what's favorable. And then add those up, and then this 5.3 would be second. Okay, so I just add those up. All right, let's do that real quick. 10.7 plus 23.3 plus 23.5 plus 55.3 plus 26.8. I get 139.6. All right, so I punched this in to simplify it, which would just be 1396 to 53. That's what it would simplify to, which is this one B. Okay, you can't see it's not on the screen, but it's answer choice B. All right, what about this one? 21. At a local racetrack, the favorite in a horse race has the odds of 5 to 3 of winning. What's the probability? All right, so this is what's favorable. That's on top. I add these together for the total. That'd be 5/8. So I simplify that 0.625 right there. D. Okay. 22. Now this is a clever one here. Talking about complementary events. Okay. Complementary events. All right, if you add an event with its complementary, it's going to equal 1. So there's one there. There should be 3 of these. All right. Here's the other 2 right here. The probability of the complement of the event is 1 minus the probability of that event. Or the probability of the event is 1 minus the complement of that event. So here's the 3 formulas. Make sure you understand these. What I could have done, I could subtract this on both sides, see? It makes this go away, and the probability of the event is 1 minus the probability of the complement of the event. Okay, which gives me this one. And I could have subtracted this one instead of that one, and I would have had these just reversed, which would be A. So there's my 3 answers. Okay, what about 23 right here? 12 of the 100 DVD recorders in the inventory are known to be defective. What is the probability you randomly select a DVR that is not defective? All right, so if there's 12 that are defective, 100 minus 12 is 88. That means there's 88 that are not defective. That's what's favorable here for us out of 100 total. So it'd be 88 over 100. Okay. All right, going on number 24. The probability that the event will happen is this right here. Find the probability that the event will not happen. All right, that's going to be 1 minus that, which is 7 over 37. Okay. 25. The probability the event will not happen is this. Find the probability that the event will happen. All right, it's going to be 1 minus that, which is 0.35. Okay. All right, 26. A restaurant offers a $12 dinner special that has 4 choices for an appetizer, 11 choices for an entree, and 3 choices for a dessert. How many different meals are available when you select an appetizer? All right, so you got an appetizer, you got an entree, you got a dessert. All right, you have 11 entrees, you have 4 choices for appetizer, and you have 3 choices for a dessert. So you multiply these together. So 4 times 11 is 44, and 44 times 3 is 132. 132 ways. Okay? That's the fundamental accounting principle. 27. The realtor uses a lock to store the keys to the house that's for sale. The access code for the lock consists of 6 digits. All right, here, I wrote this in the way here, so let me bring another piece of paper. So it has 1, 2, 3, 4, 5, 6 digits. Okay? Now, it tells us first digit cannot be 1, and the last digit must be odd. So this cannot be 1, which means there's only 9 choices for the first digit. This last one must be odd, which you got 1, 3, 5, 7, or 9. There's 5 of those. The rest of these, we're good to go. So multiply these up. That's going to be 9 times 5 is 45 times these 10s, 450,000. Okay. All right, what about 28 here? Probability experiment consists of rolling a 6-sided die. Find the probability of the unit below. Rolling a number less than 6. All right, 1, 2, 3, 4, or 5. These are all less than 6. There's 5 of those out of 6 total. There's my probability. It says do it as a decimal. All right, so I just got to do 5 divided by 6, and I get that 0.833. So that'd be 0.833. It says 3 places. Okay, number 29 here. We got a little table over here. All right, companies conducting a survey to determine how prepared people are for long-term power outage, natural disaster, or terrorist attack. The frequency distribution on the right shows the results. Use the table to answer the following question. What's the probability that the next person surveyed is very prepared? All right, there's 246 very prepared. That's what's desired. Out of the total, we add all these up. So let me add them. 246 plus 980 plus 558 plus 343 plus, plus 40. And there's my total, 2167. All right, round 3 places, so we're going to have to divide this. And there you go. So it's going to be 0.114. The 5 is going to make, look here, the 5 makes the 3 go up to a 4. And there you go. Okay. All right, what about 30? 30, we got us a little frequency table over here. Use the frequency distribution on the right, which shows the number of voters in millions according to age. To find the probability of the voter chosen at random is in this given range. 25 and 30 between, or not. Oh, I almost messed up. Not between 25 and 34. All right, so here's 25 and 34, so not would be all these other ones. That's what's desired here. All right, so I add up all these other ones. 7.7 plus 11.5 plus 22.7 plus 51.4 plus 27.4, and that gives me 120.7. Okay, total, well, I have that, add that one in for the total, 141.5, and now divide those. Okay, so, oops, my paper fell. So I'm going to type in 120.7 divided by 141.5, and that comes up to 853, 3 places. 853. Okay, I think we're in good shape there. All right, go to the next one, 31. Got another frequency table. We want not between 21 and 24. So 21, 24 is this. I do the same exact thing. Do the same exact thing I just did for the previous problem. Okay, so I'm going to have 7.2 plus 22.3 plus 26.6 plus 53.1 plus 26.8, and there's what's desired right there, 136. All these that are, except for this one. Now I add that one on, and this is my total. Okay, and so now I divide those. All right, so I'm going to do 136 divide by 147.7, and I get this right here, 0.920. See, this 7 makes that 0 go up to 1, 0.921. I should put the 0 in front, I guess. Okay. All right, we're in good shape. All right, now let's go to this one here, number 32. The access code for a garage door consists of 3 digits. Each digit can be any number of 0 through 6, and each digit can be repeated. Find the number of possible access codes. All right, so it has 3 digits. Each digit can be any number from 0 through 6. So there's 6 possibilities here, 6 possibilities there, 6 possibilities there. So the number of different codes, I multiply them, it's 216. Okay. Now, what's the probability by randomly selecting the correct access code on the first try? Well, on the first try, you got 1 chance out of that, out of 216. So I divide that. 1 divided by 216. All right, so it looks like 6 makes the 4 go up to 5. 0.005. Okay. All right. Now, part C here. I messed up. I just looked at my answer and I made a mistake here. 0 through 6, there's 7 of those. 0 through 6 is 7. It's not 1 through 6, it's 0 through 6. So this should be 7, 7, and 7, which is 343. Made a mistake there. So this would be 1 over 343. Okay. So 1 divided by 343 would be this. So it's going to be the 9 makes the 2 go up to 3, 003. Okay, I just looked at the answer and saw I didn't have it right. So don't do this. So here's a good learning experience here. Don't make sure 0 through 6, you put 7. There's 7 of those. So you got 0, 1, 2, 3, 4, 5, 6. There's 7. 7 of them. Okay. All right, now, what's the probability of not selecting the correct access code? All right, it's going to be 1 minus this. 1 minus that right there, which is going to be 0.997. Okay. All right. 33. You are planning a 3-day trip to Seattle, Washington in October. Use the fact that on each day it could either be sunny or rainy, and that each day is equally likely to be sunny or rainy. To answer the question, what's the probability that it's sunny all 3 days? So we have all 3 days there. So the probability that it's sunny, it's a 1/2. That's a 1/2, and that's a 1/2. So I multiply these together. That's going to be a 1/8. Okay? Or I type it as a decimal, which would be 125. 1 divided by 8 is 0.125. Okay, 34. What's probably that it rains on at least 1 day? All right, look here. Rains at least 1 day. That's going to be 1 minus that it's sunny all 3 days. See, we've talked about this. These are complements. When it's at least 1 day, it's 1 minus the complement of that, which we just did the complement right there, 125. So I do 1 minus 0.125, which is 0.875. Okay. All right, we're good to go. All right, 35 here. All right, we see this little bar graph shows the highest level of education received by employees of the company. To find the probability that the highest level of education for an employee chosen at random is A. So here's A, right here, 7. There's 7 of those out of how many total? So I add all these up. All right, so let's see here. That's going to be 26 and 7 would be 33 plus 37 is 70, 86, 91, 93. 7 out of 93. All right, so I divide that. 7 divided by 93, and I get, oh, it went on. Clear it. 7 divided by 93. All right, I get 0.07526. All right, the nearest thousandth, which is these 3 digits there, the 2 does not make the 5 go up, so 0.075. Okay. All right, let's go here. Classify these as independent or dependent. All right, the events of getting 2 aces when 2 cards are drawn from a playing deck and the first card is replaced. So if it's replaced, it's independent. Because if I take the card out and I put it back, then the next card has the same probabilities. If I don't put it back, that would be dependent. All right, classify this one. Event A, a red candy is selected from a package with 30 colored candies and eaten. Event B, the blue candy is selected from the same package and eaten. All right, we're not putting them back, we're eating them, so that's dependent. So the probability of this second one depends on what was picked the first time. So this is dependent. 38. You're dealt 2 cards successfully without replacement. Without replacement. All right, find the probability the first card is a 2, the second card is a 10. So the probability that I get a 2, and then the probability I get a 10. All right, when I get that 2, there's 4 2s out of 52 total. But I'm not replacing it. So the probability of getting 10, there's 4 10s, but now there's only 51 because I did not replace it. So times these. Okay, so 4 divided by 52 times 4 divided by 51. Okay, looks like 0.006, which is A. Okay. 39, the probability of answering the 2 multiple choice questions correctly. If random guesses are made, assume the questions of each have 5 choices for the answer. Only one of the choices is correct. So you have 2 questions here. All right, this is independent because whatever answer here on this question has nothing to do with what the probability will be for that question. All right, but there's 5 choices, so there's 1 correct choice out of 5 for this one. There's 1 correct choice out of 5 for that one. So I multiply these, which is going to be 1 over 25, which is 0.04. Right there, B. Okay. Now 40. Flipping an 8-sided die that includes numbers 1 through 8 and spinning a 4-colored spinner that has equal chances of getting colors blue, red, yellow, and green. What's probably you roll a 3 and spin the color blue? Is this dependent or independent? Okay, so probably you get a 3, and then the probability that we spin blue. All right, so 3, there's 1 3 out of 8. Blue, there's 1 blue out of 4 colors. So I multiply these, which is 1 over 32. So it's 1 over 32, which is one of these. Now, is this dependent or is this independent? This is independent. Because what I do here does not affect what I do there. These do not affect each other. Okay, about 41. All right, same thing. We get this, the die and the spinner. All right, what's probably you roll a multiple of 4, so probability multiple of 4, and then spin red or green. All right, multiple of 4, you got 4 and you got 8. These are the only multiples of 4 in the numbers 1 through 8. So there's 2 of those out of 8. On this one, there's 2 colors here, red and green, out of 4. So I multiply these, which is going to be 1 over 8. Okay, I did that multiplying in my head. So it's 1/8. And again, these are independent. So it's going to be A up here. They're independent. They don't affect each other. All right, what about this one? You draw a card from 52 cards. Then you draw a second card without replacing. So this is dependent. The second one depends on what the first one was. So we know these 2 are out right there. It's not those. It's got to be one of these 2 dependent ones. All right, so we got the probability of getting an ace, then the probability of getting an ace again. So the first one, there's 4 aces and there's 52 total. The second one, now once I've drawn that first one, now there's only 3 aces and there's 51 total. So I multiply those. Okay, so when I multiply those, 4 divided by 52 times 3 divided by 51, and that comes up to 0. Okay, now what's a fraction? So there it is, 1 over 221. So what's this first one? Right there. Okay. What about this one? Same thing, you're drawing from the cards, but this time you replace the card, so this is independent. So these 2 are out. It's got to be one of the independent ones. Okay, so we're doing the same thing. Probably getting an ace, probably getting an ace. So on this one, there's 4 aces out of 52. But we're going to put it back. So this is 4 aces out of 52 again. So I times these. All right, so 4 divided by 52 times 4 divided by 52. There you go. Change it to a fraction. My calculator just hit that. And it's going to be 1 over 169. There's my answer right there, which is this one, D. Okay. 44, we're getting close. 44 here. We're dealt 3 cards successively without replacement from a standard deck of 52 playing cards. The probability that all 3 cards are aces. Okay, without replacement. So you got a probability you got an ace, probability you got an ace, probability you got an ace. So there's 4 aces out of 52 total, but you're not replacing it. So that means for this next card, there's 3 aces left and 51 total. But you're not replacing it, which means now this last card, there's only 2 aces and there's 50 total. So I multiply all 3 of those. And it wants it as a decimal this time, so. All right, so 4 divided by 52 times 3 divided by 51 times 2 divided by 50. And there it is. Now this e negative 4 means this moves back 4 places. So it's going to be 0.123018099 is what I'm getting here. Okay, which looks like this right here, D. 3 zeros, 18. Okay. 45. A man has 4 $20 bills, 2 $10 bills, 3 $5 bills, and 6 $1 bills. Find the probability that the man pulls out a 10 and then a 5 to pay for his lunch. All right, so he's not putting them back, it don't sound like. So, probability that he gets a 10, then the probability that he gets a 5. All right, so if you look at your 10, there's 2 10s out of, let's see here, you got 4, 5, 6, 7, 8, 9, 15 total. All right, now the probability pulls out a 5, well, there's 3 of those. And now once I pulled this 10 out, there's only 14 total. So I multiply these together. Okay, so this, look here, you can just do some canceling like we did when we were in grade school or middle school, 1 over 35. Hey, you can just punch me in the calculator though if you can't do that. It's no big deal. All right, 46. Okay. List an example of 2 events that are independent. All right, here's some events here. Which one of these are independent? I think it's right here, rolling a die twice. When I roll it the first time, it's not going to affect what I get the second time. A father having hazel eyes, a daughter having hazel eyes, that would affect this one. Not putting money in a parking meter and getting a parking ticket, that would affect this. Selecting a queen from a standard deck, not replacing it. When you don't replace it, that's dependent. So here's the independent one. Now down here, find two events that are dependent. We already talked about that. That's independent. All right, drawing one card from certain, not replacing it. All right, this is dependent right here. When you don't replace it, that's dependent. So the answer would be C. Look here. On this one, C, you're replacing it. You're selecting the ball, and then you replace it. Tossing a coin and getting ahead, then rolling a 6. See, tossing a coin is not going to affect my die. So the answer would be C down there. Okay. All right, almost done here. This is number 47. Okay. Probably that a person in the United States has type B blood is 7%. 4 unrelated people in the United States are selected at random. Complete parts A through D. Find the probability that all 4 have type B blood. So all 4 have type B blood, which is 0.07, 0.07, 0.07, 0.07. So multiply those. Or I can go 0.07 to the 4th power. All right. So this -5 moves this back 5 places, which would be 0.123424001. That's what I would get right there. Okay, so if all 4 of them have type B blood, it'd be this. Let me check my answer there. Yeah, that's right. That's right. That's my answer. All right, find the probability that none of them have type B blood. All right, if it's 0.07 that they do, if I do 1 minus 0.07, I get 0.93. That's the probability that they don't. So find the probability that none of the 4 have type B blood. So I'm going to do 1, 2, 3, 4. I'm going to put 0.93. All right. So I'm going to do 0.93 to the 4th power, which is 0.748. Okay. Looking at my answers on here, that's right. Now part C, find the probability that at least one or more of the 4 has type B blood. All right, that's 1 minus the complement, which this is the complement right here. None of them are type B blood. Okay, so I'm going to do 1 minus this. 1 minus 0.748, which is 0.252. There you go. Okay. And then part D is asking, which of these events can be considered unusual? Well, I'd say this one right here is unusual. It's like almost 0. So the part A would be unusual. All right, last question, number 48. Okay, doctor gives a patient a 60% chance of surviving bypass surgery after a heart attack. If the patient survives this surgery, then the patient has a 35% chance that the heart damage will heal. Find the probability that a patient survives this surgery and the heart damage heals. So survives and heals. These are my 2 events. So this is 0.60, this is 0.35, and I just multiply those together. So .60 times 0.35, I'm getting 0.21. And that's right. Okay, so I went through every problem. These are going to be on the test. So if you need help, let me know. I'll help you all I can. Have a good rest of the day.